Hey, welcome everyone to this week's Physics Meets ML. We're very happy to have Luisa Lucie-Smith here today with us, and she will tell us about explainable deep learning models for cosmological structure formation. And yeah, before we get started, Luisa is currently a research fellow at the Max Planck Institute for Astrophysics here in Munich, or respectively in Garching. And she works a lot on cosmology, and in particular also using machine learning to get new insights into this. And in particular, I'm very interested about this explainable sides of things. And this is what she will tell us about today. So we're very much looking forward to your talk, Luisa. Please take it away.
All right. Thank you so much, Sven, for the invitation. So I'm really happy today to be telling you a bit about some work we've been doing with some people at UCL, Hiranya Paris, Andrew Ponson, and also some people at Stanford and UChicago, all trying to basically see whether we can use machine learning and deep learning to try to learn something new about cosmological structure formation. Okay, so I wanted to start by saying that, at least in the context of astrophysics, machine learning has actually become a kind of a traditional approach in many pipelines of cosmological inference. So it's, for example, being used a lot in classification, for example, classification of stars or galaxies in observational data, as well as regression problems. So, for example, trying to infer the photometric redshift of galaxies, again, from data. Lately, it's also been used a lot in the context of data and model emulation. So this is basically trying to construct machine learning models that can act as surrogates to very computationally expensive models like numerical simulations and so on. And it's been really effective at trying to cut down the computational cost of these models. And then it's been used for clustering analysis, outlier detections, also in observational data, and so on. And what we've been trying to do is something slightly different, where we've actually been trying to see whether we can use machine learning for knowledge extraction. So this basically means, I mean, we have this tool that we know it's very good at learning complex nonlinear relationships. So can we actually learn something new about the underlying physics if we can understand how it learns and what is it learning? Can we actually learn something new about physics? And at least in my opinion, the requirements for this idea of knowledge extraction from machine learning basically involves two things. The first one is interpretability, which basically means trying to understand why the machine learning model made a certain prediction. So this is basically trying to produce outputs that can tell us what the algorithm is learning and why it's predicting a certain thing given some input. And the second requirement is that of explainability. So this basically means trying to use whatever interpretable tool you found to try to map this interpretation onto existing knowledge in the relevant science domain. So at least in my opinion, there's no such thing as explainable AI in general. Explainability is always tied to the relevant science domain. And this also means that not all interpretability tools will work in all science domains. So it's really two things that go together in order to satisfy this or to do this knowledge extraction from machine learning. Now, the problem is that the most predictive and complex models that we have on the market are also the ones that are least interpretable. So for example, if you take a very simple model like a linear regression model or decision trees, these are very interpretable, but they're also limited to linear relationships or simple binary decisions. On the other hand, if you go to deep neural networks and convolutional neural networks, you basically have the ability to extract very complex nonlinear patterns from the data, but this goes at the cost of millions of parameters in your model, making it hard to understand what features is extracted and how those features relate to a given prediction. And so basically trying to satisfy my requirements for knowledge extraction, yet using the most predictive models that we have in the deep learning group of models is quite a challenge in the machine learning community. And so this is basically what we've been trying to do in some of my research, is to try to make progress into turning convolutional neural networks more onto the interpretable side and trying to use the most predictive models and making them more interpretable. Okay, so the context in which I'm interested in developing these interpretable models is within cosmology and cosmological structure formation. So our standard model of cosmology is actually very successful at describing the evolution of matter in the universe. So the basic idea is that you start off at very early times with some very small perturbations in the density of matter. And then as these perturbations evolve through cosmic time and under the action of gravity, these tiny perturbations grow more and more, forming what we observe as today's large-scale structure. So you can see that basically these tiny perturbations end up being highly overdense regions of dark matter that are connected by these filamentary structures and surrounded by more empty, these whiter regions are more empty regions that we call cosmic voids. So basically all the structure that we observe today originated in some way from these small density perturbations at early times. And in cosmology, we're actually quite lucky because we know what the properties of these initial perturbations are very well. And this is thanks to observations of the cosmic microwave background, which really form the bedrock of our standard model of cosmology. So on the left panel here, what I'm showing is a map of the temperature fluctuations of the cosmic microwave background at very early times. So you can think of this basically as a picture of what the universe looked like when it was basically born. So very, very early times. And so to make sense of these kinds of maps in terms of cosmology, what we typically do is that we compress the information in these maps, in these millions of pixels, into a power spectrum that basically tells us about the power of these fluctuations on different scales. And basically this is what I'm showing in this right panel. It's the power spectrum of these temperature anisotropies in the cosmic microwave background. And basically the red dots are the data, and the blue line is the theoretical predictions of our best fit cosmological model. And you can see how at large scales, the errors are dominated by cosmic variance, but as we go to smaller scales, the error bars are so small that you basically can't see them in these dots. And so this basically shows how well our cosmological model is in agreement with our data. And it turns out remarkably that the universe can actually be described just by 6 parameters that describe the content of the universe, its geometry, and properties of the initial conditions. So from, for cosmological structure formation, this is great because it means that we know what these initial density perturbations look like really well. And it turns out that they can be very well described just by a Gaussian random field with a known power spectrum that comes exactly from the temperature power spectrums of the CMB. Okay, so given that we know our initial conditions really well, and we know that the structure formation is a highly nonlinear process, what we typically do, and our best tool really to compute the fully nonlinear evolution of matter, is to run numerical simulations. So what you're seeing on the left panel is basically the evolution of the dark matter in the universe, which is most of the matter content of the universe. And on the right panel, you see basically the evolution of the stars and how these trace the underlying dark matter. And so you basically can see how throughout the simulations, these large overdense regions of dark matter grow more and more. And you start forming basically more overdense regions that merge via merging events of multiple halos. We call these halos of dark matter, and by constant accreting material. And so this is why it's highly nonlinear, right? Because you have these constant accretion and mergers with smaller structures. And you can see how basically this large scale structure becomes more and more overdense in halos, and you have these filaments, and around it, these empty regions of voids. And really, the dark matter is what forms the building blocks of the whole large scale structure. And really, you can see how the stars in the right panel just kind of form within the largest overdense regions of the dark matter. And so understanding how these halos form and evolve is really a fundamental question to then link to galaxies and then to observational data. Okay, so numerical simulations have really been fundamental in our understanding of structure formation. And in particular, they've revealed a number of key properties of our large scale structure. And I just wanted to highlight a few examples here. So what we found from high resolution numerical simulations is, for example, that you can re-express the halo abundance as a function of mass in a way that is fundamentally independent of your cosmological model and of your epoch. Similarly, we found that if you take halos that have over 20 orders of magnitude in mass, so super large, massive cluster halos and tiny ones, they seem to have the same density structure. So the distribution of matter within those halos seem to have a very similar density structure. So this is what is shown in this panel, where all the different lines show basically the density as a function of radius inside the halo for halos that have completely different masses, like 20 orders of magnitude difference. So this really suggests that it's something about the gravitational collapse process, something fundamental about gravity that leads to halos of self-similar density structure. Similarly, we found that the clustering of dark matter halos tend to depend on the time that they were formed. So older halos tend to cluster much more tightly than younger halos. You can see here how older halos tend to be more clustered, more tightly clustered, and residing in these overdense filamentary structures, whereas younger halos that are these green dots tend to be a bit more scattered throughout the sky. And so the point is that I know that despite our ability to run these numerical simulations, we still don't have a full physical understanding of why these phenomena emerge from the simulations. So, you know how I was saying that explainability is an issue in machine learning actually turns out to be an issue in our current structure formation models as well. So despite the fact that we know everything that goes into our simulation, so gravity, all the microphysical laws, we yet don't have an explanation for why halos have self-similar structures, halos of very different mass. Why do halos cluster differently depending on when they were formed? So this is sort of the kind of phenomena that I call emergent from simulations that we yet don't have an explanation for. And in this talk, I will primarily focus on the density structure of dark matter halos. So essentially, we've seen from the N-body simulation video that halos form throughout a number of very complex nonlinear physical processes. You have mergers with smaller halos, you have accreting material, and so on. And basically, the density structure of these dark matter halos contain key cosmological information. And so the simplest way to characterize this density structure is just to take the mean density in spherical shells as a function of radius. So this is what we call the density profiles of dark matter halos. And this is just an example of what these typically look like. So you have on the y-axis the density, and on the x-axis the radius, so the distance from the center of the halo. And typically what simulations revealed is that these density profiles tend to decline with radius. typically with a slope of about -1 in the inner region, and then they steepen to a slope of about -3 as you get closer to the boundary of a halo, which I am going to typically call R200 or Vera radius. And typically what we think is that the inner profile is kind of dominated by material that is well virialized inside the halo, that's orbiting inside the halo. Whereas the outskirts, as you move towards the outskirts, the density profile is instead dominated by infalling material that is being accreted onto the halo. And so our current best models to describe these density profiles of halos are really just based on empirically found fitting functions. So one of the most popular fitting functions that is used basically by everyone for decades is the NFW profile. So this is basically a 2-parameter model that essentially describes this general slope of -1 in the inner profile and -3 in the outer profile. And the NISTO is just a correction of the NFW to basically account for discrepancy in the inner profile. Now, these NFW or NISTO profiles were really designed to fit profiles within this halo boundary, right, within this R200M. But if you look at it in the outskirts, you see that there are deviations between what we observe in simulations and what the NFW profile, for example, would predict. And in particular, if we plot this in this right panel as the slope of the profile as a function of radius, you can again see that in the inner profile, you have a slope of about -1. This goes to about -3 as you approach the boundary, but then there's a steepening of these profiles compared to what is predicted by NFW. And again, this steepening carries a lot of cosmological information, is typically thought to depend on the location of the splashback radius of the halos, which is basically where material reaches the first apocenter in the first orbit. And again, this kind of steepening feature is really just being currently modeled through fitting functions that, for example, depend on the mass accretion rate onto the halo. And so the first thing that we wanted to figure out is, okay, can machine learning actually provide some physical insights into the origin of these halo profiles? And in this situation, we were actually able to use simpler, more interpretable models such as gradient boosted trees, because given featurized versions of the data, so features, we could already provide powerful insights into this kind of question. Okay, so what we did in this case was to basically construct a machine learning framework to predict the final halo profile. So in this case, I typically use interchangeably halo mass profile or halo density profile because they have a one-to-one mapping between the two. So in this case, we came up with a series of features that we wanted to test. So the first set of features is basically what the halo looks like in the initial conditions. So we can just basically trace back what the location of the halo in the initial conditions and look at the properties of the density within this region that we call the proto-halo. The second set of features describe the assembly history of the halo. So this is basically the mass of the halo as a function of time. And so given these features, we could then use them as input to a simpler machine learning model, such as gradient boosted trees, to then predict the final halo mass profile. And in this case, we wanted to really test the role of these specific features. So the initial conditions in the assembly history in determining the final halo profiles. So the nice thing about gradient boosted trees is, as I said before, is that they're interpretable. So you can actually measure how important the different features that you provided to the machine learning model, how important these are in determining your final output, so in determining the final profile. So as probably most of you know, gradient boosted trees are basically an ensemble of decision trees, which add trees in an iterative manner so that new trees tend to correct the mistake of the previous trees. And so you carry on in this iterative process to the point where adding new trees basically has no impact in your model error. And so then you've reached enough trees for the model to converge. And so the way we measure these feature importances is to look at basically every decision that is made in every decision trees of the ensemble. And for example, in this example here, where you have a feature that didn't perform very well at distinguishing between blue and red stars, so that it made a decision where the blue and red stars are equally distributed in the two child nodes, we basically have a small decrease in the model error due to the split. And so this basically assigns a low feature importance to this feature. On the other hand, if you have a situation where a feature is very good at distinguishing between your red and blue stars, then you would have a large decrease in the model error. And in this case, you would assign to that feature a high importance. And so basically, the feature importances are therefore proportional to the decrease in error from all splits made by a certain feature. Okay, so what we did is that we looked at what are the importances of our two sets of features in determining the final halo profile. So what I have here on the y-axis is basically the importances of the density around the center of this proto-halo region as a function of radius. So what this tells us is basically how important is the density as a function of scale from the center of the proto-halo region. And what we found is that there are basically two characteristic scales that determine the final profile of a halo. So if you look at the top panel here, these are the importances of the features for the inner profile, so the inner region, the final inner region of the halo. And as we go down through all the way to the bottom panel, we have the importances of those same features, but in predicting the outer profile, so the profile in the outskirts of the halo. And what we find is that the density basically on scales just below the proto-halo size are basically the most important, carry the most important information to predict the inner profile of the halo. But as you go towards the outskirts of the halo, we basically have a second feature that picks up importance, describing basically the environment in which these proto-halo live. So the density outside this RL, the density outside the proto-halo region. And so thanks to this feature importance, we were able to identify that there are two primary scales in the initial conditions that affect the profile of the dark matter halos in different ways. Similarly, we then looked at the importances of the assembly history in determining the final profile. So again, this is basically the mass of the halo as a function of time. And so what I'm showing here on the y-axis is the importances of the mass as a function of time. And in this case, we find that there are three characteristic time scales in the assembly history of the halo that then determine the halo's final profile. The first time scale is really the time where the halo formed for the first time. So basically, this is the time where the halo was formed initially. So it's the earliest time here. And it basically captures the impacts of the orbiting material that is virialized in equilibrium and orbiting inside the halo. And on the other hand, the other two peaks are instead some basically capture the importances of late time infalling materials. So this is basically the dynamically unrelaxed component of the halo that is basically capturing that material that is infalling and accreting onto the halo. So again, these kinds of simpler models were actually able to tell us some powerful, constraints on what are the characteristic timescales that are important to predict the final profile of a halo. And in particular, what this told us is that really in a halo, the orbiting material and this infalling material should really be characterized by separate components, and they are really characterized and formed in a different way, and so affect the profile in a different way.
Can I ask a quick question on this? So now there are lots of other bumps, right, in principle around. So there's some threshold, right, that you kind of put on. Is there somewhat how to put it, and how do you come to the decision that there are two important features?
Yeah, I mean, basically this is just a statistical significance of it, basically. I mean, we see that the other thing is that all these features are correlated. So basically you can also try to remove certain features to try to play around with that correlation to see whether these peaks disappear or don't, depending on what features you get rid of. And so basically what we found is that there is a slight hint here, a bump, and this basically actually reflects this the correlation with this formation time peak. Because, a halo just doesn't just form at a given time, right? It first forms the inner part, then it forms the outer part. So it's a way to describe a complex process into 3 different timescales, but of course these are correlated throughout a range of times. Yeah,
that makes sense.
Yeah. Okay, so essentially what this has shown is that features importances in ensemble methods like gradient boosted trees that can enable interpretability. If you're interested in testing the role of specific features, for example, like us, the initial conditions and the assembly history in determining the final halo profile. On the other hand, the limited predictive power of this method is that it still requires humans to come up with relevant features of the data, right? So we still had to have some idea of how density profiles should form. And so we had some idea on what features to extract about the initial conditions and what about the assembly history we wanted to test in the origin of halo profiles. And so the next thing we wanted to do is to say, okay, can we actually turn these more complex neural networks, which extract features themselves, in this project to discover basically the independent components of the density profile. So I already hinted at the fact that what our previous results showed us is that there's really 2 components, one regarding the orbiting and one regarding the infalling material inside the halos. And so we really wanted to see whether we can use neural networks to discover what are the independent degrees of freedom, or what are the independent components that are required to describe the density profile of a halo. Okay, so how would one go on about designing a deep learning model for this idea of knowledge extraction? So Aitin and some other collaborators of theirs in Zurich had basically this idea of starting from, okay, how do humans learn? How do humans learn? What we typically do is that we have a bunch of observations. This can be some high dimensional data or a whole load of observations that we gather. And what we typically do as physicists is that we try to compress these observations into a low dimensional simple representation, so that if in the future you would ask me a question or some query about that physical system, I should be able to give an answer just based on the just based on a simple representation. So for example, in this case, if you have as observations a bunch of particle trajectories as positions as a function of time, you would typically try to compress those observations into the initial position and the velocity of those trajectories, so that if you ask me where would the particle end up at some other time t prime, I can give you an answer for that just based on the representation. And so what they wanted to do is to translate this idea of human learning into a neural network model. So they came up with this model that they call SciNet, where you have basically as inputs your set of observations, and then you want to basically compress the information within those observations into a latent or a small low-dimensional representation, so that if you ask me a question about those observations, I should be able to give an answer just based on the latent representation. So this is basically translating that idea of human learning into a neural network, so that the model that does the compression from the observation to the latent space and the model that does the prediction of the answer from the latent space are both parameterized as neural networks. And what they've shown in their paper is that basically this kind of model works very well for learning the relevant physical parameters of, for example, toy 1D problems. So in this case, they showed that, for example, a neural network, so the SciNet, was able to recover the two physical parameters that are relevant for a damped pendulum. And so what they've shown is that basically for toy 1D problems where you already know what the physical relevant quantities are, the neural network was able to recover or rediscover those physically relevant quantities. Okay, so what we wanted to do is something similar, but for our density profiles problem. So for us, the observations are really coming from the whole 3D density field around the center of a dark matter halo. So from the simulation, this is what we get, right? We have a 3D simulations with many different halos. So for us, our observation is some sub-box around the center of a dark matter halo, where each pixel gives you basically the density around that halo. So that's sort of our raw observations. And what we want to get out of that is the density profile, so the density as a function of radius. So in our case, the query is the radius, and we want to have a neural network that can predict the density as a function of any given radius r. So what we did is that we basically constructed what we called an interpretable variational encoder. So you have on the left side here a 3D convolution neural networks, because our data is inherently in 3D, that basically compresses all the information in the 3D density field into a very low dimensional latent representation. And then from this latent representation, you then have just a fully connected artificial neural network that predicts the density as a function of any radius r. And so the key property of this network is really the fact that the latent representation retains all the information used by the model to predict rho as a function of any r. And so the fact that you can compress all that information in a very low dimensional representation means that if you can then interpret what is in this representation, you can then discover what are the independent components, or what are the independent degrees of freedom that are required to predict rho as a function of r. So if you compare this to what we typically do to get a density profile, you have basically on the right side here, this is just the standard analytic NFW fitting function, right? So the decoder in our case plays the role of the fitting function, which returns rho as a function of any r, given a best fit set of parameters of that model. So in our case, the decoder makes its predictions based on the best fit latent representation for a given halo, whereas in our standard, how you would typically fit, a fitting function, you would have your best fit, two parameters of the NFW function. On the other hand, what's very different here is the fact that in the interpretable variation encoder case, you're really doing this compression based on the raw density field. So you're starting from all the information that there is, and you're trying to compress that using this 3D CNN that can extract features of that data and map them onto this low dimension latent representation. On the other hand, when you do this for the standard empirical fitting function, you actually have to pre-process the data in itself to give you the halo density profile in the first place, and then perform some sort of fitting procedure like a chi-square to get the best fit parameters here. And so really the advantage of the method is that you can basically do the compression, like the model is forced to learn the latent representation from the rawest three-dimensional density field.
There's a question in the chat, which is asking, can we understand interpretable variational encoder as a conditional variational autoencoder where the query corresponds to the condition?
Yes, but the fundamental thing is also that in standard variational autoencoders, it's an unsupervised setting, right? So you typically the decoder would act to reconstruct the input. Whereas in this case, it's really in a supervised setting where the latent representation doesn't need to encode all the information about the output, but just that to predict rho. So yes, it's a conditional in the sense that it's conditional on the query, but it's also supervised in the sense that it's asked to only retain information about a particular property of interest or a particular compression of this data.
Another question maybe to follow up is like on the latent representation, do you kind of disentangle the different variables, or can they be
Yes, so I will get to that. That's a key part of the framework. Otherwise, you wouldn't be able to do interpretability. Yeah. So let me move to that. So let's look into more detail, like what this latent representation actually looks like. And it is in fact very similar to autoencoders, but again, the point is that the latent representation only needs to retain information about rho of R and not all the information in the input to reconstruct it. And so what we have is, again, the input on the left-hand side, which is this three-dimensional density field centered at the center of the halo. And what the encoder is really doing is that it's predicting the mean and the standard deviation of Gaussian distribution. So that each latent is basically parameterized in this case as a Gaussian distribution. And so the encoder essentially needs to learn what the mean and the standard deviation of each Gaussian latent is. And the idea is that since then these latent parameters are actually distributions, what you can do is that you can sample from these distributions to actually obtain a distribution for rho of R. So different possible realizations of what the density profile of the halo looks like, given the latent distributions. And so the key really in achieving interpretability of this latent space is for it to be disentangled. So this essentially means that independent factors of variation in the profile should be captured by independent or different latents. And so we are basically trying to see, this is why what the model is trying to learn is really the independent degrees of freedom, because if your latent space is disentangled, every latent will capture an independent factor of variation of the profile. If instead the latent space is entangled, well, you would basically not be able to distinguish what factors of variation influence the final profile. So in a similar way to the beta VAE, so the beta variational autoencoders, we try to encourage disentanglement in this latent space via the loss function, and then measure the degree of disentanglement via mutual information between the latents. So this is what the loss function looks like. You basically have one term that is the predictive term that we just picked to be a mean squared error. So we assume that the likelihood is Gaussian. And so then your predictive term just ends up being a mean squared error, capturing basically how close your predictions are to the ground truth. The second term in the loss function is basically what tries to encourage the disentanglement. So this is the KL divergence between the learned latent distribution. So this is the multivariate Gaussian that we've chosen as our latent distribution, and a set of priors. And in this case, we chose our priors to be unit Gaussians, so that what the model tries to do is to basically promote latent distributions that is as close as possible to a set of independent unit Gaussians. And this doesn't strictly impose disentanglement, but encourages it by trying to basically form a latent distribution that is complete, but as independent as possible. And to then actually measure quantitatively the level of disentanglement in the latent space, we use mutual information. So mutual information is basically our key quantity in interpretability, as you'll see in the next slide, but we use it even to measure the level of disentanglement. So mutual information is a known difficult measure to compute, and what we use in this paper is basically trying to estimate the density distribution via kernel density estimate. But we are
sorry, why just unit Gaussians? Why was the unit one?
So I mean mean 0 and variance 1. So it's not necessary to do that, but you can choose whatever variance you want. But basically, we found that A, for our problem, parameterizing latent distribution as Gaussians was good enough, and that B, our choice of prior was also good enough to promote the disentanglement. But you can, of course, extend this to different prior models and different distributions for your latents. It could be Cauchy, or it could be something with broader tails. It could be whatever you want. Yeah.
Thanks.
Okay, so then these are what basically the predictions for our density, just looking at the time, our density profiles look like. So we ended up having to have two models, one that basically predicts the density profile up to this halo boundary. And that's because we really wanted to compare apples to apples with NFW that we know is only really good at predicting the profiles up to the Vera radius. And what you find here is just two different examples of what the predicted and the true profiles of dark matter halos look like. So the data points here are the true profiles of the halos, and the two colored bands are essentially what the distribution of possible realizations from the latent space, of the possible density profiles from our IVE, from our interpretable variational encoder. And you can see that it's basically trying to find some sort of smooth prediction, some sort of smooth representation of this density profile, similar to what is found by the NFW profile, at least up to the scales that we can trust NFW on. Okay, so once we had a model that actually produced reliable predictions, we moved on to interpreting the information content in the latent representation. And again, our main interpretability tool was mutual information. So what we did was to compute the mutual information between each latent and the density as a function of radius. So it's the mutual information between the latent and the ground truth density, which basically tells us what information is captured by each latent about the ground truth. And so what you're seeing here, for example, in this left panel is a case where we have a two-dimensional latent space. And the blue curve shows the mutual information between latent A, so the first latent, and the density as a function of radius. And you can see that basically latent A captures information about the profile within its boundary. It peaks at about 0.3 of this R200 of this halo boundary, and then it declines as it goes towards the outskirts of the halos, where then latent B picks up, captures the information or the factor of variation in the density profile. The middle panel then shows a case where we have a three-dimensional latent space. So in this case, we again have one latent that captures this sort of inner profile variations. We have our second latent that captures the variation in the outskirts of the halo. And then we have a third latent that now captures some sort of variability that is happening close to the halo boundary. This is latent C, this yellow one. The right panel then shows a case of four-dimensional latent space. And then in this case, we see that once we add a fourth latent, this basically carries no mutual information, no information about the final density profile. And so basically what this tells us is that three parameters are sufficient to capture the variation in the final density profiles. And in particular, that these three latents capture information about the inner profile, about something around the boundaries of the halo, and about the outskirts, the outer profile. So then to try to understand more of what information these latent parameters are capturing about the profile, what we did is that we took the three latents and systematically varied one latent at a time while fixing the other two. And so what I'm showing you here is what happens if you vary the value of latent A and what happens to the predicted profile for that halo. And so you can see that this latent A that is capturing the information about the inner profile as the orbiting material region, it's really capturing information about the normalization of that profile. So if you vary the latent, you vary somewhat the normalization of the profile in the inner region. Now, latent B, which was the one capturing information about the outer profile, if you vary that while fixing the other two, you can really see how it's capturing the slope of the density profile in the outskirts. And if you remember from the beginning, the beginning of my talk, this is basically the effect of that splashback feature that changes the steepening of the profile in the outskirts of the halo. Then latent C was the one that's capturing information around or just below the boundary of the halo. And you can see that it's really capturing the slope of that inner region. So you can see that if you vary the latent, it's changing the slope of the profile. And so this basically allowed us to, together with the mutual information, understand that there are three factors of variation in the density profiles of halos. One is the normalization, one is the slope of the inner profile, and the third captures this outer slope or the splashback feature of the halos. And finally, what we also did is that we could then compare the information captured by the latents with the information captured by the two parameters of the NFW fitting functions. And so what we found is that the latent A, the one capturing the normalization of the profile, has very high mutual information with one of the parameters of NFW, R200. Latent C, what's capturing the inner shape of the profile, also has a fairly high mutual information with the other parameter, whereas latent B, which is the one capturing information about the outer shape, so the splashback radius, where the NFW is really not designed to fit the profiles, has some residual information with R200, so with the halo boundary, but basically the two parameters of the NFW don't have much information about that outer shape. And so basically, to conclude, we have this model that discovered these 3 independent degrees of freedom, 2 of which resemble somewhat the ones found by NFW, and the 3 finding an additional factor of variation given by the splashback radius. Okay, so let me just conclude by saying that, you know, there are interpretable, simpler machine learning models like gradient boosted trees that can still provide powerful insights in cases where you want to test the role of specific features. So in our case, it revealed what are the most important scales of the initial conditions and time scales of the assembly history of a halo in determining the final profile. On the other hand, something like an interpretable variational encoder, we found was able to actually discover the independent degrees of freedom in the dark matter density profiles from the raw 3-dimensional data. And so I think that something like the IVE framework that is really built on this idea of compressing information into a low, simple latent representation together with the interpretability tool of mutual information can potentially enable machine learning driven discovery in the context of cosmological structure formation. So thanks very much, and I'm happy to take questions.
Yeah, thanks a lot for this very interesting talk. There's one question in the chat. Either you can ask it directly or I can also read it out.
I just wanted to ask, how did the performance of the model change when you got rid of the 4th latent? You started with 4 latents, but realized only 3 were really correlated with the output variable. And
yeah.
So, did
so basically what I found was that the 3D latent space and the 4D latent space gave consistent predictions in terms of the accuracy of the model, but the 2D latent space had larger error bars. And this is because it didn't have enough flexibility to capture this extra information.
Okay, thank you.
Have you played around with getting an analytic formula out of what your what essentially your neural network is capturing? So because so somewhat getting an analog for NFW as a formula, so to say, effectively out of
So you mean with something like symbolic regression?
Yes,
or...
yes, please. Yeah.
Yes, so actually, yes, we did try, and it's just, I don't see personally symbolic regression as an interpretability tool. I agree that it can be helpful just to give you a fitting function, but then just the fact that you have to basically choose the complexity as a function of operator. I mean, the whole thing is so degenerate that if you really only care about the fitting function, then maybe you might as well modify NFW and try to include more parameters. I mean, you could just not care about having independent degrees of freedom, right? If you just care about fitting it as well as possible. So we did try, but I think you could basically get anything out of it, right? Depending on what operators you choose and what complexity you choose. So it didn't really shed much light. Let's put it that way.
Okay. Are there any more questions? Please feel free to, raise your hand. Or there's a hand. Yeah.
Hi.
Yeah.
Sorry. Yeah. I had a question. First of all, thank you for the presentation. It was very helpful and interesting. I had a basic question about the types of machine learning models that can be used to model halos. I wanted to ask if you have tried or thought about using physics-informed neural networks to solve the PDEs themselves and model the solution with that.
To solve what, sorry? Oh, the
partial differential equation.
I see.
Yes.
No, so I haven't played much actually with these physics-informed models. And I think that they are a very nice alternative, way of putting in physics that we know. And so inherently that also becomes more interpretable because it satisfies certain properties by construction. I think I find it, I think that in my opinion, the least information I give to the neural network, the more in principle I can discover new things from it. So in the context of PDEs, that makes total sense. In the context of trying to understand how, for example, these emergent properties of logical structure arise, I mean, although there are, of course, symmetries in the problem and conservation of mass and so on, I think that introducing our own knowledge can basically bias the discoveries of the neural network into something that we already know. And so I would prefer designing models that satisfy those models, not by construction, but because it discovered something sensible.
That makes sense. Thank you.
Yeah.
I had a small follow-up question. If you could elaborate a little bit on the NFW model and how it works.
Mm-hmm. Yeah, so it's just a fitting function. So this is it. Is this fitting function here that NFW, the people that the name comes from, just stared at a whole bunch of profiles in halos, and then they were like, oh, this double parallel can, fit this function. And so it's really empirically found fitting function with two parameters, these RS and ρs. And it turns out that it fits quite well in specific ranges, but it of course misses a lot of the information specifically in the outskirts of the halo. So it's really a simple two-parameter empirically found fitting function.
Makes sense. Thank you.
Any more questions? I can ask another one. So can you envision a little bit, whether if one gives up the independence, so if you allow, say, two latents be correlated or so, are there potentially gains that you can make out of this? So in the sense of, going away from just having, independent Gaussians, but like allowing for certain dependencies?
Well, what would happen is that you wouldn't be able to know how many degrees of freedom you have, right? So in principle, you can continue enlarging the dimensionality of your latent space because everything's correlated with everything. So, you could have a 4D, 5D, 6D latent space, right? Because they're all just sharing information, they're all correlated. So you would lose information about the dimensionality of the problem that is really interesting per se. And also these curves wouldn't make much sense, right? Because then they would all be sort of overlapping depending on how correlated they are. I mean, you could probably, do you see what I mean? Like this computing the mutual information between one latent and your output really only makes sense if that latent has its own independent information, right? Like if they're correlated, then I'm not sure you could be able to infer any of the things we have inferred, including the dimensionality in the problem. And what are these independent factors of variation? Like something like this, you would basically see everything changing with everything, right?
Yes, I mean, I would think one could do something like with two, like, okay, I would still like in terms of the dimensionality, I mean, one can start slow, right? In terms of having just two together and then see what is going to happen.
Yeah, but then you just add more and more latents and everything would look fine, right?
Yeah. No, instead of like having 4 latents, so keep 4 latents, but they correlate latent A and B, right? So don't have them as independent Gaussian, but have them as a multivariate Gaussian, essentially.
Yeah.
And see whether that makes a difference of the.
I mean, I looked a lot at these because getting the disentanglement wasn't so easy. So most of the plots I looked at, the features, the latents were entangled, and you really just, I think, can't infer much because you just don't know what is capturing what. Like these plots would make no sense because everything's changing. I do think that for the interpretability, disentanglement is crucial. Yeah. And this is also why I'm working on extensions of mutual information estimators to actually train a neural network to minimize mutual information rather than just encourage it via these beta VAE logs.
Yeah.
Yeah.
I can see no more urgent questions. So yeah, let's thank Luisa again for a very nice talk.